Hello, my name is Naoto Matsubara from University of Tsukuba, Japan. Today, I'm going to talk about VR interface for designing multi-view camera layout in a large-scale space. First, let me show you a video of the VR interface for designing multi-view camera layout that summarizes our developed system. This interface simulates the suitable placement of many multi-view cameras depending on various shooting situations on a 3D CVIM model. As you see, it is difficult to decide where to place each camera appropriately when capturing with a large number of cameras called multi-view video shooting in a large-scale space such as a soccer stadium. Therefore, it should be useful if we could know the placement of the cameras before going to the shooting site. This is our motivation to realize this interface. This interface has a variety of features to help the user decide where to place the cameras. I would like to introduce the interface from now on. Free viewpoint video makes it possible to view images from various perspectives. In recent years, it has been introduced to the field of sports, making it possible for people to watch sports in an immersive way. In order to generate free viewpoint video, multi-viewpoint video shooting is necessary. As shown in the figure, multiple cameras are arranged to surround the shooting space, and the images from each camera are combined to generate a free viewpoint video. The problems with multi-viewpoint video shooting in large-scale spaces is that it is necessary to handle the large number of cameras, the large number of camera parameters to be set, such as camera zoom, position, and orientation, as well as the variety of preference for video observation at the same time. In order to tackle with these problems, it takes a lot of time and labor. So we think that simulating camera placement on a 3D model of the stadium in advance improves the operational efficiency of multi-view video shooting. In order to realize the camera placement simulation, there are two items to be developed: multi-view camera placement interface and creating 3D models of the stadium. Here is an overview of our research following steps from previous slide. The red box represents the creation of a 3D model, and the blue box represents multi-view camera placement interface. First, starting from the figure at the top left, we take pictures of the stadium, for example using a drone, when we go to the real stadium for the site inspection. Then a 3D model of the stadium from the aerial images is created. The created 3D model is imported into the multi-view camera placement interface to simulate the multi-view camera placement on the 3D model. The camera placement is displayed on the 3D model based on the input criteria for generating free viewpoint video. This allows us to define how the stadium is being filmed from each camera. Once the placement is determined, we use the information to arrange the cameras at the real site and capture the target scene without spending much time and labor. Next, I will talk about multi-view camera placement interface. Here is how the interface works. The user inputs two kinds of requirements: shooting requirements for multi-view camera and observation requirements for viewing the generated video. After the input is completed, parameters such as the position and orientation of each camera to be placed and the camera angle are estimated. Based on the calculated parameters, the camera icons are placed on the 3D model to display the multi-viewpoint camera placement. Next, I will explain more detail about the input interface. The first step of the input is to enter the shooting conditions. The parameters of the virtual camera are set to match the specifications of the real camera used for real shooting. After that, a 3D model of the target stadium is placed. In this figure, we use a model of a stadium found from the internet. It has accurate 3D shape information. Finally, each requirement numerically in the entry fields is entered as shown at the bottom right of the figure. These requirements include the area of the field to be shot, the spatial resolution of the image, the area on the stadium where the camera will be placed, and the angle from which the image will be shot. The blue rectangle at the right is the area to be photographed, and the center of the rectangle is the shooting point. After entering the conditions, the camera placement will be shown on the 3D model. The recommended camera placement is displayed by placing camera icons on the 3D model in this way. Each camera is positioned so that the depression angle of all cameras and the convergence angle between the cameras are constant. From the shooting point, the vectors are extended to each camera one by one. Also, the camera icons placed in the figure are colored in 4 colors: red, green, blue, and black, to represent each camera status. Green means that the field of view is narrow to cover the full shooting area, denoted by the blue rectangle. So you need to choose a lens of shorter focal length. Blue means that the spatial resolution of captured image is lower than the target value, so a camera with higher resolution is needed. Red cameras have both green and blue characteristics, while black cameras don't have any problem. Numerical values of parameters for each camera are shown on console window. The focal length shows how much you need to zoom in, and the spatial resolution shows how precisely you can capture an area of the image. As I mentioned in the previous slide, there are cameras that doesn't satisfy the requirements, such as having lower resolution and narrower field of view. Our interface has a function to recommend the suitable numerical values of the focal length and the resolution. You can also virtually observe the view from each camera by clicking on the icon. As you see in the image on the left, when you click on a camera icon, it is possible to check how the stadium is being filmed one by one, as shown on the right. It is also possible to indicate the area of the entire camera arrangement with enough spatial resolution. By switching the display style, it is possible to visualize the area that can be captured with high enough resolution to meet user requirement. Here is our demonstration video once again. First, we enter the shooting conditions in the lower right-hand column. After entering all conditions, the camera icons will be placed on the 3D model. Clicking on this red-colored button, we can switch to the spatial resolution indicating mode. Clicking on a camera, you can confirm the image captured by each camera. You can also switch the view to the camera next to it by using a keyboard or similar devices. Next, I will talk about creating 3D models of the stadium. This corresponds to the red box area of the overall figure. I will explain how to take an aerial view of a stadium from a drone and generate a 3D model of the stadium from the aerial images. Right now, we are conducting a preliminary experiment to generate a 3D model of the stadium using miniature models. In this preliminary experiment, I took multi-view images of the stadium miniature models, as shown in the figure on the right, and created a 3D model from those photos. To create a 3D model from multi-view images, I used structure from motion. This method estimates the position and pose of the captured image from multiple viewpoints and estimates the 3D point cloud from the motion parallax information between the images. Here is the process of creating a 3D model. Point cloud is generated from the multi-view images using structure from motion, and then the mesh is applied to the point cloud to create a 3D model having surface information, as shown in the figure below. The result of importing the generated 3D model into the interface is shown in the figure. The top figure shows the camera icons to be placed, and the bottom figures show how you can observe the CG Stadium model by clicking on the camera icons. In conclusion, in this research, I proposed a method to save the time and labor required for multi-view camera placement by developing an interface to automatically calculate and arrange multi-view camera placement. As a preliminary experiment for a 3D reconstruction of the real stadium, we created a 3D model of a stadium miniature model. This is the end of my presentation. Thank you for listening.